I thought I'd talk today about reduction for information theory, and I do this in the hopes of getting people from computer science who are experts at that reduction approach to help out in some problems in information theory that could really use your expertise using these reduction techniques. Now, reduction, of course, is a very old strategy. It's been used for decades, if not longer, but it's not very common in information theory. And so let me start out by a very basic definition, which to some of you will be like bread and butter, but maybe not to everybody. So just to make sure that we're all on the same page. So the idea of reduction is very simple. We imagine, and first let me say this in the computer science kind of domain, and then I'll translate to an information theory domain. In computer science, reduction is typically used in roughly the following way. We imagine that we're given two problems. I'll just call them problems A and problems B. And we imagine further that we can demonstrate that given any solution for problem A, we can build a bit of machinery such that if you combine the solution for A with that machinery, it will give you a solution for B. In that case, we say that problem B reduces to problem A. Because it's enough to solve problem A, any solution for A can be turned into a solution for B, and so you can always solve problems in B just by learning to solve problems in A. Now, typically in the CS theory literature, this is used as a way to compare complexities of two problems. So in particular, if you know that the machinery that you had to add on is not too complex, then the problem B can't be much more complex than the problem A. And so it's used to compare the complexity of problems. It sounds so simple as to be almost trivial, but in fact it's an incredibly powerful tool. And the reason that it's powerful is that you can do these arguments even if you have no idea how to solve problem A. You can still say something about how complex problems A and problems B are, their relative complexity, by comparing them to each other without actually being able to solve the complexity of either of them. And so that's where the power lies. You don't need to come up with a solution for A in order to understand the relationship between these two problems. In information theory, this technique hasn't found much use, but it can be used here in much the same way, not for complexity purposes, but for other purposes. And here's one such example. Imagine that instead of having two problems A and B, you now have two networks A and B, whose capacities you're interested in understanding. And imagine that you could show that given any sequence of codes for network A, you can build a bit of machinery such that the sequence of codes for network A plus the machinery gives you a sequence of codes for problem B. In particular, we are most interested in this relationship when there's some corresponding relationship in the performances of those codes. So for example, if the sequence of codes for A had an error probability going to 0 and some particular rate, and the sequence of codes for B has an error probability going to 0 and a related rate, some other rate that you can calculate as a function of these rates, then you can relate the capacities of these two networks. In particular, if the rates that you get on one and the rates that you get on the other are the same, you could show, for example, that the capacity of the network A is a subset or equal to the capacity of the network B, because any rates you can achieve on one, you can also achieve on the other, which is, of course, our definition of capacity. So you can get this relationship between the capacity of A and the capacity of B, and again, the power of the technique is that you need not know how to design a sequence of capacity of achieving codes, nor do you need to know what the capacity of these networks are. You can still derive a relationship between their capacities through this kind of comparative technique. Since designing codes and finding capacities is incredibly hard, especially if you're thinking about very large networks, this gives you a huge amount of power that we didn't previously have before we started applying these techniques in this domain. And let me give you an example of the kind of question you can answer and how this technique is used, just so that you can see this reduction tool in operation. So here's a very simple question that you could ask. Imagine that you have an arbitrary network, and I'll define more precisely what I mean, what kinds of networks we'll consider in the next slide. And you're interested in understanding the impact of delay on capacity. So you're going to add some finite known collection of delays at some of the outputs of this network, and you'd like to understand what the impact of adding those delays is on the capacity of the network that you're studying. And this is a question that's been asked for many years in the literature for special example networks, and the way it's tackled in each of those papers is to find the capacity of the network without the delays and find the capacity of the network with delays and compare them to each other, and then try and make some sort of statement about whether delay impacted capacity. In some cases, these statements are not very precise because they find bounds in each of the cases and then compare the bounds to each other, but they try and assess for each of these special cases whether delay impacts capacity. And these are very nice results, but you can see that if you take this approach, you'll never be able to answer the general question of whether delay affects capacity. I mean, you can study each of these examples one by one and solve more and more special cases, but first of all, solving each of them is incredibly difficult because capacities are hard to find. And second of all, it doesn't give you the opportunity to generalize, and reduction in fact does. Reduction gives you a nice opportunity to ask the question in its most general form. So let's just come up with a few definitions first to make sure that we're all in agreement as to what exactly we're asking and what our model is, and then we can tackle this question of whether delay affects capacity. So here's my network model. We'll imagine that the relationship between the inputs at each of some m nodes in your network and the outputs at each of those nodes is given by some statistical description of the conditional distribution of the outputs given the inputs, and we'll assume, for simplicity, a memoryless network. We have m nodes here, and don't think of m as 10 or 20. Think of m as large as you want. Maybe you have 1 billion nodes in your network because you're worried about delay in the internet. At each time t, the inputs and outputs at a particular node I are given by xt and yt with a superscript of that I. So I here denotes the node, and t denotes the time for that particular input and output. And the input at time t from a node I relies only on information available to that node at that time. So we'll imagine that each node has some particular source that he's interested in communicating, and if some particular node has no source, that's okay. He can just have a source of rate 0. So we'll call that source that he's interested in communicating wi, and that wi will be available a priori to that node. That is, he knows the full message that he's trying to communicate from the beginning of time. He can use that information in deciding what to communicate at time t, as well as anything he's learned from the network over the previous t-1 time steps. So this gives us a causality constraint that says that node I at time t can only use outputs from the channel that come at times 1 through t-1, not whatever is going to come out at the same time t as he transmits this value, nor certainly what will come out in future time steps. Now, if we're going to use this code, this network n times for our communication problem, the message wi, which will have some rate ri, can take on one of 2 to the nri possible messages. So this source originating at node I takes on one of 2 to the nri values if he's trying to communicate at rate ri. And likewise, each node may have a particular subset of demands. These are the sources from other nodes that he's interested in reconstructing. So di will denote which subset of the sources from other nodes he's interested in reconstructing. So if I have, say, j in this set di, it means that node I is interested in reconstructing the message from another node j. And wi hat will be the node i's reconstructions of all of the sources that he has demanded. And we'll calculate the probability of error as the union of the probability that any of our nodes get any of the messages that they're interested in reconstructing wrong. So if anybody gets anything wrong over these n channel uses, the whole system counts as an error. Even if you were close or whatever it is, you get no credit for that. And that will be included in our probability of error. And then the network capacity will simply be the collection of rates R1 through Rm. These are the rate values for our m different nodes and their corresponding sources, for which there exists a sequence of codes with probability of error going to 0. And this operation here is just a closure. This is the standard capacity definition for a memoryless network. So here's a simple result that we can derive using reduction. The result says that delay has no impact on capacity. And that applies for any memoryless network with any number m nodes, including all of the examples that were studied previously in the literature, except that in some of those cases they violate causality, and therefore our results become incomparable with theirs because of those differing assumptions. But any of the topologies there can be studied here as well. And proving that the two capacity regions are the same turns out to be very simple using this reduction technique, far, far simpler than the proofs in any of those prior papers, and here's how it goes. So we'll prove it in two parts. In the first part, we'll compare the capacity of the network with delays to the capacity of the network without delays and try and show that delays can't increase capacity. That is, the capacity region with delays is a subset or equal to the capacity of the region without delays. And I'm using, as I said, ND to represent the network with delays and N the original network without delays. I'm going to consider this only in the case with a single delay. It turns out that not only will that keep our notation simpler, but it actually is enough to prove the general result, because if the first delay has no impact and the second delay has no impact on capacity, you can easily show that no finite known collection of delays impacts your capacity. So it suffices to prove that no single delay impacts capacity. Delay will be independent of n, yes. It's one delay, and I'll show you what that looks like here in just a second. I'm drawing for you two nodes only rather than the billions of nodes that I asked you to think about previously, not because you shouldn't think about a billion, but because a billion doesn't fit nicely on a slide. Think of node 1 as the node who's suffering the delay, and node 2 as a representative of all the other nodes who are suffering no delays. You'll remember that we're adding one delay at one node in our network. Question?
Is the same delay everywhere?
I'm sorry, say it one more time.
It's the same delay all the nodes, or they may be different?
No, any node can have any number of delays. In this case, we're considering exactly one node having a delay. All the others have no delay, and he's having exactly one. By which I mean what's represented in this table. So what I'm trying to show here is what comes out at node 1 and what comes out of your network at node 2, or what's received from your network at those two nodes at each of the time steps t. And because node 1 is suffering one delay, what normally would have been received at time 1 gets received at time 2. What would have been received at time 2 gets received at time 3, and so on. Whereas node 2, which is representing all the nodes who have no delays, get everything at the time that they come out of the channel. Okay, so this table just shows what a code would look like that was built for the network with delays. So what would that code look like? At each time t, each of the nodes 1 and 2 transmit something across the network that is a function of what's known at that particular time. So at time 1, we haven't gotten anything previously from our network, so we are giving just a function of our outgoing messages at these two nodes, and what's received at time 1 by node 1 is nothing. What's received at time 1 by node 2 is y1 of 2. At time 2, again, each of these nodes has to transmit something that's a function of what's available at that time. So each one has its outgoing message. Node 1 has no information that has arrived yet from the channel. It will arrive at the same time that he transmits this value, but our causality constraint doesn't allow us to use that information. Whereas node 2 has the information that came out of the channel at time 1 at node 2. And so on. So this is some code that is usable across the network with delays, and we'd like to show that we can run that code with the same rate and the same probability of error on the network that has no delays. And of course, doing that is trivial, because if I have no delays, I have all the information that I would have had with delays, and so the same code can be run in exactly the same way. In particular, you'll notice that at time 2 here, I'm using exactly the same transmission that I used in the prior slide, despite the fact that I already received more information. I'm just going to ignore it because I want to use exactly the same code in order to demonstrate that I can get the same rate and the same probability of error, which of course I will because I'm using identically the same code. Proving the other direction, that the capacity of network N is a subset or equal to the capacity of the network ND, is a little bit harder. And the reason that you run into a problem here is because we'd like to take a code that was designed for network N and run it on network ND, and that turns out to be a little bit tricky. The challenge here is that at time 1 we can transmit exactly what would have been transmitted across network N. But because of the delay experienced by node 1, the second time transmission, which we normally would have been transmitting at time 2, can't be transmitted until time 3. We have to wait until time 3 because this output from our channel hasn't yet arrived in time to use it at time 2. We have to wait for time 3 and so on. And if you take this same logic and apply it further, you'll end up only transmitting at every other time step to get this message across. Those in-between time steps are kind of being wasted because you're waiting for the output of the channel to come so that you can use it at your next step. Of course, that leaves all of our even time steps open. And so what will we do in order to demonstrate that we can get the same rate and the same error probability asymptotically? We'll just use those even time steps to send another message. So we'll use exactly the same code, but we'll interleave its use on an independent message so that we can get the same rate, more or less, and the same error probability. Now let's be careful and make sure that the rates and error probability are exactly the same. So you'll notice that the amount of time that this is going to take us now is not 2n, but actually 2n plus 1. It's 2n plus 1 because I have to wait one extra time step to get the last channel output that my decoder is going to need to decode. So in total, it's going to take me 2n plus 1 time steps to send 2n times the old rate r bits. So we have 2n r over 2 to the n plus 1 as our rate for each of these messages. Asymptotically, that's the same rate that we would have gotten in the network that had no delays. And our error probability by the union bound is just twice the old error probability. Since the old error probability was going to 0, this one is going to 0 as well, which demonstrates that any rate that was achievable on the network with no delays is also achievable on the network with delays. Since we already had the other direction, this proves that delay has no impact on capacity. Now, just to point out again, this actually doesn't agree with all of the prior results. That is, some of them either prove or suggest that delay has an impact on capacity. In cases where they're suggesting it, it's sometimes because their bounds are loose. In cases where they're proving it, it doesn't turn out to contradict. It turns out that they're violating causality, sometimes in subtle ways, inside the way that they use these networks. And so we don't have a contradiction with these prior results, but it's interesting that it contrasts with all of these examples, every single one of which in some way suggests that delay changes your capacity, and under certain assumptions it does. Now, of course, reduction in the complexity literature is used to derive all kinds of interesting and complicated results using this very simple tool. And we'd like to do the same thing in information theory as well. So for example, you can look for equivalent problems, problems where the capacities of two networks are identical to each other, such as we have in the previous delay example. You can look for hard problems, problems that are have the same kinds of relationships, but now in a capacity sense or a code design sense. You can look for complete problems and so on in this new domain. And I'll give you some examples of what those might look like in these information theoretic problems. So just to give you a broad survey of the kinds of things that we've been doing with these reduction tools, the first things that we actually did were bounds. We were using reduction to show that the capacity region of one network was a subset or equal to the capacity region of another network. And if you do that in both directions, you might end up with relationships to networks that are not identical to each other, so you don't always get equivalences. Sometimes you'll be able to show that the capacity of one network is bounded above by that of one model and bounded below by that of another model, each of which you can either solve or find corresponding lower and upper bounds for, allowing you to get upper and lower bounds on capacities of some networks that we wouldn't have had good tools to analyze previously. And that's the first kinds of problem that we started solving with these reduction techniques. We've also been looking at equivalences. Not just we, but the community broadly has been looking at equivalence relationships. And it turns out, just like in the complexity literature, that there are a variety of different notions of equivalence that you can define. And we've defined a couple of possible definitions. I won't walk you through each of these results. If you're interested in decoding them, they're down here. But this slide is just show that we're starting to uncover some very interesting and relationships between different problems. So, for example, you need not study k unicast problems if you're interested in code design. It's enough to study 2 unicast problems, and so on. So you can derive all kinds of interesting relationships that help you reduce the space of problems that you need to study down to smaller classes whose solutions would give you solutions to everything. We've also managed to come up with some examples of what would be considered complete networks in much the corresponding definition to the definition you would use in complexity theory. And we'd like to understand whether there are more complete problems and complete problems for different classes of networks and so on. We've also uncovered what I can best describe as canonical problems, problems that turn out to be equivalent to other problems that look nothing like them, and maybe highlight some key properties of networks that we need to understand and have not been able to solve. And to give you one example of such a canonical problem, let me just state one of the problems that we've been studying in the past few years. So the problem is pretty easily stated. My network model in this case is going to be a collection of lossless links, each of which has some capacity. And the capacity of each of those lossless links may be different, but I won't label all of them. I'll label just one of them. In particular, this edge, which we'll focus on in a moment, has a capacity delta. Again, we have sources leaving some nodes and demands leaving others. You could have sources and demands at all of them. I was just keeping the picture simple here. And the question that we'd like to understand is the following. If you give me any network N of lossless capacitated links, I'd like to understand what the impact of any single edge is on the capacity of that network. So I picked a particular edge here, this edge I'll call E, and I want to understand how much does this edge of capacity E contribute to the capacity of the network as a whole. In order to understand that, I'm going to compare the capacity of this network to a capacity of another network which is identical except for the removal of that single edge of capacity D. And my goal here is to understand, well, how much do things change in order to understand the power of a capacity delta edge. Our original thought was that, well, you know, a capacity delta edge helps by about delta. And so the question that we asked is, if I tell you that some rate vector R1 through Rk is in the capacity region of the original network N, is it true that R1 minus delta through Rk minus delta is in the capacity region for network N delta? The thought here was that if you had only one source, one of these sources going across this network, at most it would be sending delta across this edge. So if you take out that edge, it would hurt that source by at most delta. Now, of course, now we have lots of sources simultaneously going across this network. But still, it seems that at most this edge is carrying delta of each of those sources. So it must be true that if you remove that edge, you hurt, in the worst case, every one of them by delta, but it should never get worse than that. Surprisingly, this question that I thought would be really easy, a matter of a week to solve, remains open. We don't actually know whether this property is always true or sometimes false. But here's a little bit of a summary as to where things stand right now. So first of all, we've been able to show that this property that I showed in the previous slide holds for some classes of networks. And the classes of networks for which it holds are mostly of the form where you can control what you put in such that what would go across this edge is always the same constant value. And in cases where you can control it in that way so that what would have gone across this edge is always that constant value, then you really don't need this edge anymore. You can run the same code on this network. You'll have a little bit lower rate because you don't get to send all message combinations, but it turns out that a simple counting argument tells you that the rates are, in the worst case, suffering by delta in each dimension. So a nice reduction argument allows you to use a code designed for this network on this network. Of course, that reduction argument only works in cases where you can manage to ensure that what would have gone across this edge is that same constant value. And in many cases, we don't know how to do that. And when we don't know how to do that, this problem is unsolved. We've shown that the property does, however, hold for every outer bound that was available, at least at the time that we were doing this work. And so if you look at capacity outer bounds for networks and you remove an edge of capacity delta, the outer bound changes by at most delta. The outer bound may be loose, so that is inconclusive about the original problem, but it's at least a little bit of evidence. But in general, the problem, as I mentioned, is unresolved, and we've tried very hard to come up with counterexamples and failed. We've tried also very hard to prove that the property always holds, and we've failed at that too. So as I've said, this problem remains unsolved in general, but we have been able to show that this problem is equivalent to lots of other problems. In fact, nowadays, every time I run into a problem I can't solve, I try and prove that it's equivalent to this problem because I seem to be stuck on the same issue again and again, and it comes down to this. For example, the edge removal question that I just posed in the previous slide turns out to be equivalent to a question about network coding, that is communicating across networks of lossless links, that asks whether when you define the capacity as all rates that you can achieve with precisely error probability 0, versus when you define the capacity as all rates that you can achieve with a probability of error going to 0, whether you get the same region. If these two definitions give you the same capacity region, it turns out that the answer to this question is always yes. If those two definitions of capacity give you different capacity regions, it turns out that the answer to this question is sometimes no. And we don't yet know which of those things is true. We have, however, proven that the problems are equivalent to each other. Now, in addition to studying this problem in the realm of networks of lossless links, we've also studied this problem in what I'll call hybrid networks, which are networks that contain some lossy components as well as some lossless links. Again, the question is the same. I want to understand whether removing a single edge of capacity delta can hurt my achievable rate by more than delta. And in this realm, actually, we have been able to solve the question. Before we solved it, though, we looked around in the literature and found that for every example that we could find in the literature that can be posed as a special case of this hybrid network and edge removal question, for example, the multiple access channel with conferencing encoders, which is a network where you have a noisy component, a multiple access channel, as well as some communication added between your transmitters. For all of the previous examples that we found that exist in the literature, or at least that we could find in the literature, that can be posed in this way, nobody had asked this question before, but you can look at what capacity regions they got when they added extra edges and compare it to the capacity regions before they had those extra edges and see that this property is always satisfied for those examples. Surprisingly, though, in this case, we actually were able to construct a counterexample. So we were able to construct an example. Again, it involves a multiple access channel, but a more complicated sort of machinery in which we're adding this extra link. And in this case, we were able to demonstrate that there exists multiple access channels for which the achievability of R1, R2 in the capacity region of a network N that contains some link of capacity delta does not imply the achievability of R1 minus delta, R2 minus delta in the network that you would get if you remove that single edge of capacity delta. And that was surprising since we've been unable to do the same in the realm of lossless links. What's even more surprising is that even if you relax this constraint a little bit and ask not whether I can get R1 minus delta and R2 minus delta when I remove that link, but even if I can get R1 minus f of delta and R2 minus f of delta for a polynomial f, it turns out still to be false. That is, we can construct counterexamples where the achievability of R1 and R2 is in the capacity region of network N does not imply that the achievability of R1 minus f and R2 minus f is in the capacity region when that edge is removed, and we can do that for any f. So we say that the impact of a single edge can be almost exponential, by which we mean that we haven't constructed an example where removing the edge hurts you by an exponential amount, but since we can get over any polynomial, it's almost at that exponential point. Now that, of course, was done by constructing really artificial counterexamples, examples designed in our attempt to break this, which of course we've done in the network coding domain as well, but in that case we failed, in this case we succeeded. But the channels that you get for these counterexamples, as I said, are incredibly unnatural. You don't expect to ever see such a channel in the real world. And so the next question was whether you ever observed this property in real kinds of networks, at least networks that people actually study in the literature as models of real communication systems. And my original thought was probably not, because our examples were so carefully constructed that I didn't think, for example, if you had a Gaussian multiple access channel, that this property would arise in that case.
So if you have y as a function of x1 and x2, a deterministic function of x1 and x2, then this conclusion doesn't hold.
If you have y as a deterministic function of x1 and x2, actually it does hold. You can construct deterministic multiple access channels, not for every one of them, but carefully constructed deterministic multiple access channels for which this property, this x, is appropriate, you know, that the implication does not hold.
I thought you were mentioning that. So, yeah, I thought that the conclusion was that you need randomization.
We don't need randomization. We need multi-terminal kinds of devices that don't exist in the network coding domain. Meaning that if you go back to these network coding kinds of realms, it's true that this node can implement any function, but showing that this property would be true would not only require this node to implement one of those bad functions, you'd need to show that every capacity achieving code does whatever that bad function you wanted to occur was. And so that's quite different than if this is a deterministic channel that does some bad function to you every time. It's just given to you that way. And in fact, it's a nice question. So in fact, deterministic models were the models that we constructed originally. And roughly what they do is the following. They make almost all pairs of x1 and x2 bad, but enough good ones in there so that if you allow them to just cooperate a little bit across this link, your two transmitters, that you can hit lots of good ones, even though almost every entry in some sort of table of entries is bad. And so that's roughly what our examples look like. And if you want more details, I'm happy to share those.
You probably need the alphabets to be large, right?
The alphabets were quite large, and in fact, if you wanted me to construct something for more and more drastic, oops, where did it go? More and more drastic versions of these polynomials, the alphabets would get larger and larger. Oh, sorry, I'm getting lost here. Yes? So you don't need memory, but you may need large alphabets, if that makes sense. So these channels, for example, are memoryless. So again, just to go back, so while we originally constructed very artificial examples of what these channels should look like, we, as a next step, went and looked at some more natural channel models, such as the Gaussian multiple access channel. And what we found for those more natural models is that not only was my intuition or my assumption wrong that, oh, this probably won't arise in natural examples. In fact, this arises, I would argue, sort of most of the time. I'm not quite sure how to quantify that, but let me make that more specific. So imagine that you look at the gain that you get by adding a single link of capacity. In this case, I labeled it C out. And I'm going to plot that gain as a function of C in, the amount of rate going into this node. This node is helping the cooperation process, so we called it the cooperation facilitator. I'm going to look at the gain as a function, as a function of C in, the amount of information going into that node, and C out, the amount of information going back to the two transmitters for your multiple access channel. And we'll define that gain as the difference between the rate R1 plus R2 that you can get when this edge is here to the rate R1 plus R2 you can get when that edge is not here. In other words, when C out is equal to 0. So that's the gain associated with this cooperation function. It's obviously a function of both C in and C out. And what we demonstrated was that if you're in a network where two nodes transmitting across this network are controlled by the same transmitter, if you had two nodes controlled by the same transmitter, you would do better than the capacity of the MAC. Then it's always true that the gain that you get by adding this opportunity to cooperate has slope equal to infinity. The rate that you get isn't necessarily this big, but anytime this value is strictly larger than the sum rate capacity of the MAC, the gain function that you get has an infinite slope at C out equals 0, which says that a little tiny edge here can have a much, much larger impact on the capacity. That slope, that trade-off between the rate that you're adding and the benefit that you're getting from that rate is actually equal to infinity at delta equals 0 for all the channels in this family. And I would argue, or at least I suspect, that these are most of the interesting channels. Multiple access channels where somebody controlling both of the inputs would do better than somebody who has to transmit across that network by using purely independent transmitters. So that brings me to my summary and conclusion. The punchline is that I think reduction is a really useful tool for information theory. It hasn't been used very much, and that means that the information theory community on average has less experience than the CS community in applying these tools. And I think it would be terrific if more of the experts in using these tools would join the effort to try and figure out what they can tell us about information theoretic problems. To give you some of the things that we've done with them so far, they allow direct solution of long-standing open questions. The delay example was one such example. They make possible a new type of unifying theory, giving us structure to the family of problems and giving us the ability to answer problems about all networks and understand when big classes of networks have related solutions, which is really hard to do when you're solving problems one at a time, which is the traditional information theoretic proof. They highlight canonical networks and canonical problems, problems whose solution would solve lots of other problems, and therefore highlight sort of important points of where we don't quite understand what's happening, and if you could figure that out, would solve lots of other questions. They can be applied to solutions and to bounds. As I showed, you can use them both to get upper and lower bounds and to get precise solutions in some cases. And maybe, I hope, they offer a good bridge between information and computation theory. So hopefully they sit right at that nexus of computer science and information theory. And that concludes my talk. Thank you.